Electric drives consist of a motor, an inverter, a speed control system, and a set of sensors. In particular, faults in inverter switches account for 31% of all faults in the industry. Open circuit faults prevent phase currents from flowing through the affected switches, leading to an overload on the remaining power devices. Over time, this can result in secondary faults within the inverter and even a total system shutdown. For this reason, the diagnosis we propose allows for the detection and isolation of both single and multiple faults when an open circuit fault occurs in any of the inverter switches. Since the amplitudes of the currents depend on the load coupled to the motor, torque variations affect the current levels. To mitigate this effect, the three-phase currents are normalized. The normalized currents are then separated into positive and negative half cycles, thus decoupling each phase current into two signals that are sensitive to faults in the upper and lower switches of a leg. Subsequently, the resulting signals are averaged over one period using a moving average filter and compared with a threshold level. If one or more of these signals drop below the threshold, a fault is reported. Finally, the activation of any fault signal indicates fault detection, while fault isolation is performed by analyzing which fault signals have been triggered. The isolation process starts after the fault is detected. This process involves analyzing the activation of the fault signals F, according to the flowchart. The activation of three fault signals indicates a fault in either two upper or two lower switches, which is classified as case 3. If two fault signals are activated, this indicates either a full leg open circuit or a cross fault, which corresponds to case 2. When only one fault signal is activated, it is classified as case 1, indicating a fault in a single switch. The final fault isolation is performed according to table, which details the diagnosis for all fault cases. The proposed method was experimentally validated under various fault conditions, including full leg open circuit faults, crossed switch faults, and simultaneous open circuit faults of the two upper switches. For example, the case of crossed switch faults is analyzed. Open circuit faults occur in switches SBU and SCL at t equals 0.038 seconds and t equals 0.073 seconds. Furthermore, in Figure A, it can be seen that after the first fault, the signal IBP decreases below D, triggering the fault signal FBP at t equals 0.047 seconds, which isolates the faulty switch, as shown in Figure B. The second fault is subsequently isolated at t equals 0.079 seconds, as shown in Figure C. For the analyzed operating point, each fault is isolated within half an electrical cycle, as shown in Figure A.